All right, ladies and gents, today we're going to start our fourth unit in grade 11 physics. And the topic of our fourth unit is waves and sound. So I think that you'll find it interesting and very applicable to things that you see around you. Let's get started. So the first topic we're going to look at is vibrations. And so I want you to just take a minute to conceptualize what your idea is of a vibration. So where in your everyday life do you see a vibration? How would you explain a vibration to somebody who maybe was not aware or understanding of the idea? Just take a minute to jot down your ideas related to that. So in science, a vibration is considered a cyclical, and we think cycle, circle, but not necessarily, a cyclical motion of an object about an equilibrium point. So let's take a look here at this animation of a pendulum swinging. So you can see this sort of, it's almost like a normal line, a perpendicular line. And that would be representative where the equilibrium point is for this pendulum. So what is an equilibrium point? It's the point sort of where if that pendulum were at rest, it would be positioned. And so it's swinging back and forth. Let's look at what one cycle in a vibration might be. So you can think about it in numerous different ways. If I were to look at it from this point over here, the left, a complete cycle would be the time it takes for it to go, or the distance it goes back and then back to its original starting point. I could also look at it from the right and measure it from here and then back again. But another way to think about it would be to measure from the equilibrium point and back. So in other words, it waves out, then back to the equilibrium position. So again, the equilibrium point is just that position where if the object that is vibrating were at rest, where would it be positioned? Here's another important definition for the beginning of our unit, waves. So my guess is that when you tried to conceptualize a vibration, the term wave came to mind. And so a wave is really just a type of vibration where there's a transfer of energy over a distance and it's some sort of a disturbance. And so that word disturbance also likely came to mind when you were thinking about vibration. So when we talk about that disturbance being transferred through a specific type of material or a medium of some description, then we call it a mechanical wave. So that, here are a couple of examples of mechanical waves. So, we think about our water wave, and we're going to talk about what's going on here in this picture with the particles, but a water wave is an example of a mechanical wave, and the disturbance is occurring through water. Whereas, a sound wave is a different type of wave. We can see, that particles of air, if air is the medium, are being compressed and expanded as it moves from the source to your ear, for example. And those are two examples of mechanical waves. So I know in your math class you've recently discussed sine waves and cosine waves, just the functions of trigonometric equations. So periodic motion likely came into the conversation. It's motion that occurs when the vibration or the oscillation of an object is repeated in equal time intervals. So if that definition doesn't quite make sense to you, let's look at some diagrams. So if we were to take the graph of this object that's on a spring, and we were to graph its displacement as a function of time, we would say that, the origin, or it's sort of the x-axis rather, would be its equilibrium position. So if I were to not bounce this object connected to a spring at all, its rest position would be along the x-axis. But as soon as we give it a little bit of energy, there's some elastic potential energy stored in that spring, it's going to start to oscillate or vibrate. And so when we map out that oscillation as a function of time, we see that it creates that sine wave that you're likely very familiar with. Incidentally, I could have plotted the same graph with the pendulum that we saw above, and we would see that same oscillating pattern. So just in case you weren't sure how to include that animation in your notes, or it moved a little bit too quickly for you, here's just another still image that you can use in order to kind of add to your notes. And so I want to take a few minutes now to talk about what is happening at the atomic or at the particle level in different types of media. So in a solid medium, such as, steel or wood or any material that is a solid, the atoms are going to be held tightly together. The forces of attraction between those particles are going to be stronger, and that holds them in this nice crystal formation. So you can imagine that any vibration that's occurring in one area of this solid, because all of these atoms or particles are connected together, that vibration is going to transmit fairly easy throughout the entire material. So a few points that I want to talk about. So because the atoms or the particles in a solid are held tightly together, we know that a vibration in one portion is going to transmit the vibration throughout that solid. Think about, I remember the commercials with the mattress where there's the bowling ball on one end and the bowling pins on the other. Well, most solid materials are not like that. You're going to experience the vibration throughout. Any medium that when experiences a disturbance is going to kind of return back to its original shape, we call that an elastic material. And in general, we would say that the stiffer the material, the more effective it is at transferring the vibrations. The quicker it is at transmitting the vibrations, and those vibrations will go further and they'll last longer. So I want to talk to you a bit about fluid media. So usually when people think about fluids, they think liquids. But the reality is that both liquids and gases are classified as fluids because they flow, and that's what qualifies a substance as a fluid. So let's take a minute to differentiate between the particles in a liquid versus the particles in a gas. So in a liquid, the particles are somewhat attracted to each other still. They're sort of sliding and slushing past each other. And so because those particles are in contact, they're going to be still fairly effective at transmitting vibrations. Here you can see the particles sort of gliding past each other. So they're still fairly close together, though they are not sort of in that crystal formation that we saw with a solid. However, the particles in a gas are super far apart relative to the particles in solids and liquids. They have a lot more energy. They're able to overcome the forces of attraction that would normally want to cause them to stick together more or to be closer together. So as a result of that, these particles are not in contact a whole lot. Now, because they're not in contact, it's really difficult to transmit a vibration through them, far less effective. So to summarize, vibrations travel super well through most solids. They travel moderately well through liquids, and they travel fairly poorly through most gases if we're comparing similar items. So I like to think of the example of, if you were to put your ear against a metal pipe, like on a fence post, say for instance, and you have somebody flick the pipe, that sound will travel really quickly to your ear, and it can be painful. If you were to, I don't know if you've ever spoken to anybody underwater, like you just dunk your head underwater and try to speak, then that vibration through the water will go more quickly, and it'll sound a little strange in comparison to through air. So here's some homework for you to work through today in order to consolidate some of the ideas. Perhaps I may be checking to see that it's completed. So make sure that you ask any questions. You can do that via Google Classroom or save your questions for Monday, and I'll be happy to work through them with you.